Hi, everybody. Welcome to another thrilling installment of Chemistry from Professor Staples' Basement. Today, we're going to talk about chemical reactions and chemical equations and look at some of the very basic introductory concepts that go along with that. And so let's begin. One of the things that we have to define before we can really get into this topic and talk about what these are a class of molecules called diatomic molecules. These are all molecules, or these are all elements that when they exist by themselves, you never find them as single elements. Rather, you find them as what we call diatomic, meaning one is bonded to the other. Oxygen, a prime example. So the oxygen that we breathe, the oxygen in the air, doesn't exist as just single oxygen atoms sort of floating around in space. They always exist as O2. And so two oxygen atoms that are bonded together with each other. The reasons for that are things that we're going to get into a little bit later in the course. But the bottom line is it has to do with these elements sort of fulfilling their desire, so to speak, of having full outer electron shells. Just like we talked about with ions, where an element, when it forms an ion, will gain or lose electrons in order to have the same configuration as a noble gas. It's a similar idea here. Not the same, but it is similar and it's related. But like I said, we'll get into more detail for that about that later on. For now, what you need to be concerned with are just the fact that these elements exist in these forms, and it's something that we are going to be running into throughout the rest of this unit and certainly throughout the rest of the semester. And so the ones that you need to be aware of are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So like I said, all of those, when they exist by themselves, and that is the important distinction there, is it's only when those elements are by themselves they'll exist as N2, N2, F2, and so forth, which is different, again, from when we talked about like ionic equations, for instance. And so Na with its 1 plus and Cl with its typical 1 minus as an ion is going to come together as NaCl. However, once again, when Cl is by itself, just pure chlorine, usually in the gas phase in normal conditions, but when it exists by itself, not in its ion form, it would always exist as Cl2. So again, there's something to be aware of and to note because we are going to be running into that throughout the rest of the semester. And so these are important to just know. If there are several ways that you can remember these. The way that I remember it is kind of weird. Is I remember hydrogen is one of them, but then the rest of them sort of make a number 7. If you start here at nitrogen, you go over and down. Start at nitrogen, then over to fluorine and down. So it's those in addition to hydrogen. And so chemical equations. When a chemical change happens, or actually even when a physical change happens, we can express that by way of a chemical equation of some sort, which shows us what's going on. We could have just a word description. For instance, I could tell you methane is going to react with oxygen, which will yield carbon dioxide and water. So I can just verbally say that is what happens, and that is how I would one way that I could define or express the reaction. But I could also write it out here as a chemical equation. We have our reactants, our methane reacting with oxygen. So remember, like I said, here's that O2 that I was talking about. There's pure oxygen existing as O2. So those are our reactants, which react together to yield, and that's really kind of what the arrow is all about. These things react together to yield our products. So in this case, we're told carbon dioxide and water. So CO2 and H2O. Don't worry about these numbers in front quite yet. These are called coefficients. We will get to those. Those are certainly a very important part of a chemical equation. But don't worry about them quite yet. For now, we're just sort of focusing in on these highlights of a chemical equation, being our reactants reacting to yield our products. And so that's a symbolic representation of a chemical reaction taking place. Quite often, we include extra detail, including the states of matter: solid, liquid, gas, and aqueous. And so pretty self-explanatory for most of those. We have CH4 in the gas phase, O2 in our gas phase, carbon dioxide in the gas phase, and H2O as a liquid. Let's just take a minute to talk about aqueous. And so AQ, standing for aqueous. Never remember how to spell aqueous, to be honest. UE. Wow, I am okay. I should have just left it. AQUEOUS. There we go. AQ equals aqueous. Recording this on a Sunday morning, not quite with it yet. Probably need another cup of coffee. And so aqueous means that the substance is dissolved in water. This is something else that we're going to get into in more detail in the next unit, actually in the very beginning of the next unit, but we're going to let's just discuss some of it right now. And so again, AQ means dissolved in water. Now we do have to note that ionic substances will behave differently from molecular or covalent substances when they dissolve in water. And so if I take a covalent substance, we'll focus on that first, just something like glucose, so C6H12O6. Let's say I have that as a solid, and I'm going to just dissolve that in a little bit of water, and I end up with C6H12O6 aqueous. And so all that's happening there is the full sugar molecule, the actual full discrete sugar molecule. And let's just take a look real quick at what a sugar molecule looks like. So here's a picture of an actual sugar molecule. This is what a molecule of glucose looks like. And so when we dissolve that in water, when we have C6H12O6 aqueous, we have this whole entire thing stays together, and water molecules just sort of surround that. Again, we'll talk about some of the logistics of that a little bit later in the course. But the point is that it's a covalent, it's a molecular substance made up of purely non-metals, carbon, oxygen, and hydrogen, all non-metals. It's a covalent or a molecular substance. And so the whole thing just stays together when it dissolves, and the water molecules surround that. That is different from how an ionic substance behaves. And for an ionic substance, and we've looked at pictures similar to this before, and I'm sorry this one's so small, but it's the best one that I could find. And so an ionic substance, when we look at the chemical formula for it, something like NaCl, that doesn't exist as a discrete molecule. It's not like I have one Na and one Cl and they're bound together like this, and this sort of floats around. Rather, the chemical formula NaCl tells us the ratio of those ions within this lattice type of structure here. And so when we dissolve this, something different happens. The whole thing does not stay together. When you dissolve an ionic substance, so if I take NaCl, if I have solid NaCl, that's an A. And again, I add H2O to make it a liquid. And so I now have NaCl AQ. So I have dissolved NaCl in my water. What this really means, what this stands for right here, is the actuality of what exists are the Na1 plus ions and the Cl1 minus ions. That's important to note. It's something that we're definitely going to be using in lab, for one thing, for those of you in CHY 114, when you are doing the conductivity lab. Conductivity is a measure of these charged particles, so we're able to see how many of these ions, or not how many of these ions, but we're able to see a measure of the charged particles in a solution. And we're going to be using it in this class. Sorry, eyes are itchy this morning. You didn't need to know that. Anyway, as far as this unit looking at reactions, it's important for us to note, because what this means is that when we dissolve an ionic substance like this, Now the Na and the Cl, those ions, the sodium 1 plus ion and the chloride 1 minus ion, are free to float around in that solution and possibly hook up with other partners, possibly find other ions that they're then going to form a new compound with. That could be a very distinct possibility, and we're going to see examples of that happening. Of essentially, I'm not sure why that keeps popping up. Stop it. Okay, all just disappeared and came back. So we'll see examples of that happening. And we also would want to note that maybe, for instance, if we have CaCl2, solid CaCl2, and we dissolve that in water, remember that, so that ratio is we have one Ca ion to two chloride ions. And so this means that what would actually exist is a Ca2 plus ion and two Cl minus ions. That's what would actually exist in water. These are known as dissociation equations, by the way. And so in the dissociation equation, we show what happens when something dissolves in water. And so in the example of an ionic substance, and so we have NaCl solid, then becomes Na1 plus aqueous and Cl1 minus aqueous, something like a polyatomic ion. So NaNO3, remember the NO3 is a polyatomic ion which does not break up. So if I have solid NaNO3, then I'm going to have Na1 plus aqueous plus NO3 1 minus aqueous. Once again, one of the reasons that it's important to be able to memorize those polyatomic ions, so that we know that we don't break up NaNO3 when it dissolves, or we don't break up NO3 rather when it dissolves in water. That NO3 stays together, but it does separate from the sodium, from the Na. Maybe we have something like aluminum phosphate. Sorry, no, that's not the example I wanted to use. I wanted to use magnesium phosphate. So it would be a formula of Mg3PO4 2. We're going to dissolve that in water. Once again, phosphate, polyatomic ion, stays together. But we have 3 of our magnesium ions. And we have 2 of our PO4 3 minus ions. So those are all ionic substances, so they'll break apart in water. However, when we look, if we did a dissociation equation for our old friend glucose, C6H12O6, that does not break up in water. And so the product side of that dissociation equation is going to illustrate that the whole molecule is still together, but it is dissolved. And so again, these are just things that we'll have to note for lab, and we're going to note it for what we talk about in a little bit when we start to look at particular types of equations and reactions and how things are breaking up and reforming and coming back together. And so that was all to really talk about aqueous. And so the rest of the states of matter are pretty self-explanatory, really. Chemical equations in general show the reactants and products in a reaction. They also show the relative amounts in a reaction. And those numbers in front are called coefficients, sometimes called stoichiometric coefficients. We're not going to worry too much about that word stoichiometry until in about a week and a half when we start getting into our stoichiometry unit. For now, we're just going to call those coefficients. And so what this means, and this in this equation, is this is 4 atoms of Al, so 4 aluminum atoms are coming together with 3 O2 molecules, and they form 2 aluminum oxide molecules, 2 Al2O3s. And we'll see where these coefficients come from in just a second. The bottom line is that they come from the law of conservation of matter. We haven't really talked about these chemical laws yet, but this is a biggie. Law of conservation of matter states that the amount of matter does not change. And so matter must be conserved over the course of a chemical reaction. which tells us that the number of atoms present at the beginning of a reaction must be exactly equal to the number of atoms present at the end of a reaction. Now, what we have to remember as well, like I had mentioned earlier, chemical reactions are sort of all about things coming together in new combinations, coming together in ways that didn't exist before. The products represent a completely different combination of atoms than the reactants do. And so the amounts that are needed in each case might change. However, we're still bound by the law of conservation of matter. Let's take a quick look back at this example here. And so we know that aluminum, when it exists by itself, can exist as simply Al. So aluminum is just going to exist by itself as aluminum, just one aluminum atom floating around. We also know that oxygen, remember, exists as a diatomic molecule. So it's going to exist as O2. Now, when those are going to come together to form aluminum oxide, we have to remember the rules that we talked about when we're creating an ionic formula. So remember, aluminum with its 3+ charge and oxygen with its 2- charge. Now, again, let's make a distinction and let's recognize that this is not the same as this. This is an O2 molecule, 2 oxygen atoms linked together. We don't think of this in terms of charges. We don't think of this in terms of a 2-. This is just 2 oxygen atoms linked together. This is our oxide ion. 2 different things from each other, and we have to keep that in mind. And so the point of that is that we know that when Al3+ comes together with O2-, we have a chemical formula. Accidentally chose highlight there, evidently. There we go. That means that we're going to have a chemical formula of Al2O3. And so we need Al2O3 over here on our product side. Now we have a problem, right? Law of conservation of mass tells us that the number of atoms cannot change. We have 1 aluminum here, but now we have 2 over here. Where did that extra aluminum come from? Can't just come from the sky, can't come from nowhere. Same with oxygen. 2 oxygens over here in our O2 molecule. We have 3 over here. That extra oxygen can't just come from nowhere. It can't just appear magically because we need it to. So we're going to talk about how we account for that, how we account for the law of conservation of matter within our chemical equations. Let's look at a simpler example. The creation of water, creation of H2O. Once again, we know that hydrogen exists as a diatomic molecule, so it's going to exist as H2. Oxygen also exists as a diatomic molecule, so it's going to exist as O2. Those are going to come together to form H2O. We know that's the chemical formula of water, so that has to be the chemical formula. So we would look at these and we would count these and we would say, okay, I've got 2 hydrogens over here on my reactant side, and I've got 2 hydrogens over here on my product side. That's okay. We would say that the hydrogens are balanced. We have a balanced amount, the same number on each side of our reaction. Oxygens, however, we have 2 over here on our reactant side and only 1 over here on our product side. That's a problem. Those are not balanced. So we need to fix that somehow. The temptation is to just fix it like this. Say, okay, well, I'm just going to go ahead and throw another 2 right here. Then I've got the same number on both sides. I've got 2 hydrogens on my reactant side, 2 oxygens on my reactant side, 2 hydrogens on my product side, 2 oxygens on my product side. Beautiful, I've taken care of it. Hopefully you see what the problem is there. The problem is that we can't just change the chemical formula of water. We know water is H2O. We can't change that. H2O2, hydrogen peroxide, what your mother used to make you scream with when she would pour it on your cuts when you were a little kid. So very different things. So we can't simply add a subscript in order to balance out our equation. Cannot do that. Makes it a completely different molecule. And so what we can do instead is, instead of saying that I'm going to make 1 water molecule, we say I'm going to make 2. And we illustrate that we have 2 by putting a 2 in front. That's our coefficient. The coefficient tells us that I've formed now 2 entire water molecules. So now you can see with those 2 entire water molecules, I have 2 oxygen atoms over here. But look at what that did to my hydrogen. Now I've got 4 hydrogens on my product side and only 2 on my reactant side. And so I'm also going to say that I'm going to bring 2 hydrogen molecules to the party. Now the whole thing is balanced. This is what's known as balancing an equation. We balance equations to be sure that we have the same number of each type of element on both sides of the equation. I'm going to repeat that. Balancing an equation means that we have the same number of each type of element on both sides of the equation. That's all there is to it. Some of them are going to be complicated, and you're going to find that you go back and forth, and we're going to look at a few examples. But that really is all there is to it, is making sure that you have that same number of each type of element on both sides. And again, it arises because we have different combinations of elements in our products as we might have in our reactants. Those new combinations sometimes mean that we're going to have a different number of each type of element on each side. And so we adjust for that, we correct for that by having different numbers of the whole entire molecule represented with a coefficient in front. Let's take a look at an example here. So here we have sodium chloride plus magnesium bromide forming sodium bromide and magnesium chloride. This is a double displacement reaction, by the way. We'll talk about what that means in a little bit. But first, we're just concerned about our balancing right now. So we can go through this and we can see that, okay, in my products, or my reactant side rather, I've got 1 Na and 1 Cl, and I've got 1 magnesium and 2 bromines, Br2. But then over here on my product side, I've got 1 sodium, 1 bromine, 1 magnesium, and 2 chlorides. So we can see that my bromine, or my bromides and my chlorides, are not balanced. I've got 2 bromides over here and only 1 here, 1 chloride over here, and 2 over here. And so you could fix either one, doesn't matter which one you do first. Remember that we cannot simply do this. We cannot simply add a 2 here and a 2 here. Those are not how sodium and chlorine come together, or how sodium and bromine come together. So we cannot simply do that. What we do is place a 2 in front of our NaCl and a 2 in front of our NaBr. Now I have a balanced equation. I have the same number of each type of element on both sides. Several strategies to balancing equations, but a few things to remember is that, like I've said a few times now, once the equation is written, the subscripts cannot be changed. Do not mess with those subscripts after you've determined what they are. Instead, we use our coefficients to balance the equation. A few different sorts of rules and steps you can think of. You'll find that as you do more of these, you're just going to develop your own flow and your own pattern. But we'll first have the equation of our reactants and our products, sometimes including physical states, sometimes not. A good rule of thumb is if you're given information about the physical states, include it. We'll find with some particular reactions we are going to need those, but sometimes you won't see them represented just because they're not necessarily important for the information we're trying to convey. One approach is to then first start with balancing the compound that has the most elements in it. So whatever you see that has the most, balance that one. Elements that are on their own, such as maybe an O2, save that for last. And then we sort of check to see that everything adds up. Do I have the same number of elements of each type of element on both sides? If, as you're going through, you end up in a situation when you're done that you can simplify by dividing each of the coefficients by a whole number, then you can do that. And that you might run into situations like that here and there, depending on just your process as you're balancing. Trial and error. One of the honestly, is pretty much the method that I use. When you see that you have to balance an equation, you just sort of find something that needs to be balanced. Do that. That might then affect something else in the equation. Fix that. And then you might find yourself going back and forth a little bit until you get it. Let's take a look. Here we have an example. So CaCO3 decomposing into CaO and CO2. One calcium on each side, one carbon on each side, and 3 oxygens. So this one's balanced as it's written. We don't have to do anything with it. It's already balanced. But now we have here the combustion of ethane. C2H6 plus O2 gives us CO2 and H2O. So we can go through and do our counts, and we can see that our carbons aren't balanced, our hydrogens aren't balanced, our oxygens aren't balanced, everything's out of whack here. And so we're going to balance oxygen last. That's by itself. So we're going to save that one for last. That'll help us out. And so one place to start is to do H first, sort of because that changed the most. So you could do that. So we're going to put a 3 here in front of our H2O. That gives us 6 hydrogens on the product side. And we had 6 on the reactant side. So that takes care of our hydrogens. But then we can see that we run into a problem. We can see that because of this, it's an O2 here. The only way we can adjust our oxygens is by putting a number in front here as a coefficient. That's only ever going to leave us with an even number of oxygens. But now this side has an odd number. That's going to give us a problem down the line. One way that you can fix that is by just doubling that right to begin with. So we're going to have 6 H2O instead. But then we see, okay, well, what did that now do to my number of hydrogens? Now I've got 12, which means I'm going to need 2 of my C2H6s. Okay, so I'm going to need to put a 2 there to take care of my number of hydrogens. So I'm at this scenario now. We do our counts. And so we can see now that we're gonna have to change our number of carbons or adjust that. We have 4 carbons over here on our reactant side, only 1 over here on our product side. We put a 4 there to take care of that. Finally, we can take care of our oxygen. 4 times 2 is 8, plus 6, we have 14 oxygens over here. So we can put a 7 there, and now we're finally balanced. Just thinking about another approach, just another way to think of this. And so same exact equation, we're just going to run through it again in a slightly different way. If we just choose to balance the largest molecule first, take care of our C2H6, then we're going to put a 2 in front of our CO2 and a 3 in front of our H2O. So that takes care of balancing. This now is balanced with our products. Then if we look at our oxygens, we can see that that's not balanced. Now, what you would be tempted to do, what you might be tempted to do is say, well, if I put a 3.5 for here, 3.5 times O2 is 7 oxygens. That takes care of it. That balances it. We can't have fractional coefficients, though. That's a rule that I'm going to change on you in a couple months, but for now, we cannot have fractional coefficients. Now, it is absolutely fine, though, if as you're working, you get to this step and you say, okay, well, I'm going to put a 3.5 here just for now, just as a placeholder, because I know that would take care of it. That's okay. Because what you can do when you get to that point, if you get to a point where you say, oh, if I could just put something 0.5 here, it takes care of everything for me, then go ahead and do that, but then just recognize that if you just double everything in the equation, that would then take care of it for you. So you've got your 3.5 here. And so you say to yourself, all right, well, I'm just going to double everything. So we go to 2 C2H6s, our 3.5 doubles to 7, our 2 doubles to 4, and our 3 doubles to 6. And there we have it. All right, pause the video here and go ahead and practice these. Remember that your goal is to have the same number of each type of atom on both sides of your equation. And you're going to do that by adding coefficients in front of all of the equations. So pause the video now and see what you can do. Okay, and now really actually pause the video and really try these. Give these a whirl, practice these, see what you can come up with. That was for those of you that didn't really pause the video and do it, which I know is probably about half of you. Okay, so hopefully you're back and you were able to come up with these answers. If you didn't, go back and check. If you have something and you say to yourself, why doesn't this work? I swear this is balanced. Then just do that basic check of seeing, do I have the same number of each type of atom on both sides? That's our basic goal in balancing. Now we're just going to talk about 5 basic chemical reaction types. There are more than these, and there are different ways to categorize chemical reactions as well. In fact, many of the different types of chemical reactions that we talk about later in the semester could actually be included into one of these classifications. But this is one way for us to very broadly categorize some chemical reactions so that we're able to start to predict what some products might be, knowing the reaction type. So synthesis, easiest one. In a synthesis reaction, 2 or more elements come together to form a compound. And so an example, sodium and chlorine coming together to form NaCl. Now, once again, noting that difference of how things are coming together in new ways, in new combinations. And so sodium, which can exist just completely by itself, plus chlorine, which is a diatomic, so it will exist as Cl2. When those come together, we look at our rules for how ions are going to come together. So an Na1 plus and a Cl1 minus, those are going to come together as NaCl. So there's our product, but then we have to look at the balancing. Then we have to say to ourselves, okay, I've got 1 Na here and 1 here, that's all right. 2 Cl's here and only 1 here. That's a problem I need to fix. I can fix that by saying I'm going to form 2 NaCl's. But now that messed with my number of sodiums. I've got 2 sodiums now on my product side, only 1 on my reactant side. So a 2 right there in front of my Na reactant, and I have a balanced equation. And so we've already worked through one of these, but try the other one. Pause the video now and try the aluminum plus bromine, see what you can come up with. Hopefully you came up with these. Decomposition reactions, the exact opposite. Now we have a compound that is splitting into its constituent elements. Now again, when we do that, we have to keep in mind what form elements are in when they exist by themselves. And so this example here, our H2O. So we have H2O that is going to split into hydrogen, which we know is a diatomic, so that must be H2. It's also going to split into oxygen, which again we know is a diatomic, so must exist as O2. Then we have to look at our balancing. 2 hydrogens in my reactant side, 2 hydrogens in my product side, so that's fine. 1 oxygen and 2 oxygens, so that's not fine. We're going to fix that by saying that we're going to start with 2 waters. Now I have 4 hydrogens in my reactant side, so I'm going to put a 2 here and have 4 hydrogens in my product side. And now that's a balanced equation. So same idea, pause the video here, come up with some balanced equations for the decomposition of these substances. Again, keeping in mind what form an element is going to exist in when it is by itself. Is it okay if it exists alone, or is it on our list of diatomics? If it is on our list of diatomics, then it must exist as whatever the element is, with a 2 as a subscript. Let's pause the video here, give these a run, and see what you can do. Hopefully you came up with these balanced equations. The next type of reaction is called a single displacement reaction. In a single displacement reaction, one element basically kicks another one out and forms a compound instead. And so here we have here A plus BC. So we have A by itself and BC are in a compound. And so A is going to come in and essentially kick out B. Let's sort of just let's draw that a little bit differently. There we go. Okay. And so we have A plus BC in a reaction. And so A is going to come right in and kick B out completely. And so now AC will be together and B will be off by itself. Couple things that you have to note here is that AC are there's a good chance that they're going to come together in a different way than what BC did. So you're going to have to come up with what the new chemical formula would be for AC using the rules that we've talked about. You have to also consider the identity of B and if it is something that is going to exist as a diatomic molecule or not. And if it is, then you would have to adjust for that. The other thing to note here is that polyatomic ions, once again, will always stay together. Those are not going to be broken apart. And so let's look at an example. Let's say I have maybe some aluminum plus some copper 2 chloride, CuCl2. And so I've got these two things coming together. Now, if you're wondering what's going to kick out what and what your new combinations are going to be, you're always going to form a new cation anion combination. And so we look at these and we would say, okay, aluminum, when it forms an ion, is going to be a 3 plus. I said this was copper 2, so we know it's a 2 plus. We also know it's a 2 plus because we know chloride is a 1 minus and we have 2. So that means that copper must be a 2 plus here. And so, like I said, we know it's going to be our new cation anion combination. Our new plus minus combination is going to come together. So that's going to be aluminum and chlorine, which tells us that our new formula over here is going to be AlCl3. And copper is now going to be by itself. It is not on our list of diatomics, and so we're fine to write it just as is, just like this. And as you're starting these out, I would do these exactly like I did here. Write out your charges up above. We'll see where that also comes in handy with double displacement reactions in a second. But write these up above to help you determine what the new chemical formula of your new product is going to be. And so we have another example here of zinc plus sodium nitrate. So we can see that the zinc comes in, kicks out the sodium, leading us to a new chemical formula. Zinc has a 2 plus charge, nitrate has a 1 minus charge. So we have ZnNO3 2. Sodium is now by itself, and if you go through and balance it, you end up finding that you end up needing a 2 in front of your Na and a 2 in front of your NaNO3. So try these out. Pause the video now, give these a try, see what you can do. I hope you got these balanced equations. Double displacement reactions, very, very similar. Only now you've got two different ionic formulas as your reactants, two different cation anion combinations, and they're just going to completely mix and form new combinations on the other side. And so we can see that happening here. We have AB plus CD. And so let's look at that in terms of our charges. We have AB plus CD is going to then form AD plus CB. Now, without even knowing what the numbers are, so this is all just very generic. But so without putting in numbers, just looking at what the type of charge is going to be. Remember, we always write things as cation first and then anion. So we know that A is positive, B is negative, C is positive, and D is negative. And so we have those two new combinations. A is going to come together with D. So there's our AD. We also know that C is going to come together with B. There's another cation anion combination. So we get CB. So just completely mixing up and coming together with our different combinations. Now, the reason that this happens goes back to what we talked about in the very beginning. That if we think these are all ionic substances, and so we take AB as a solid, we dissolve it, and now we have A minus and B positive. Sorry. We have A with a positive charge and B with a negative charge. The same thing would happen with CD. That's a solid. We dissolve it. Now we have C with its positive charge and D with its negative charge. So we have all four of these ions that are now just floating around in solution. And so, since we have these four different ions floating around in solution, there are two different possibilities for new cation anion combinations that did not exist before. So all these four ions are just floating around in there. And so if AD finds each other, then we can have an A coming together with a D. I really don't know why that keeps popping up today. I'm sorry about that. Or if CB find each other, there's our new plus minus combination. And so that's the first thing to do, is to recognize, okay, which ions are going to be coming back together with which in order to form our products. The other thing that you have to do, though, and this isn't illustrated here because we didn't put any actual charges on these, the other thing that we have to do is to come up with what the new formulas are going to be. Let's walk through this example. So we have magnesium chloride and sodium phosphate. We have MgCl2. I'm not going to put in the states just for ease and quickness. So MgCl2 plus Na3PO4. So again, I would definitely recommend going through and writing out what the ionic charges are going to be. We know magnesium is a 2 plus, chloride is a 1 minus, sodium is a 1 plus, PO4 is a 3 minus. And so if we start to look at our new combinations, we have one new combination is our magnesium coming together with our phosphate. So that's Mg with a 2 plus charge, PO4 with a 3 minus charge. When those come together, it's going to be Mg3, PO4 2. So that's one of our new products. Our other possibility is if the Na comes together with the Cl. So that's Na with a 1 plus and Cl with a 1 minus. And we know those are going to come together as NaCl. So there's our other product. And so now we have our products. Let's just clean this up a little bit. Oop. Eraser head. There we go. Just to make this a little bit neater for us, I would, yeah, and I'll just remove the charges. There. So now we have our full chemical formula, or our full chemical equation, but it's not balanced. So we still need to balance this because we have different combinations leading to new ratios. So we have to balance it and make sure that we end up with the same number of each type of element on both sides. And so when I start to look through this, I say, okay, 1 magnesium here, 3 here. All right, I'm just going to fix that. So I'm going to put 3 in front of my, that's part of it. My iPad screen isn't the best. That's a 3. There we go. Sorry about that, but that's 3 MgCl2s. Now let's look at what that did to my number of chlorines. Now I have 6 chlorines in my reactant side, only 1 in my product side. So I'm going to put a 6 right here to fix that. Now I say, okay, well, that leaves me with 6 NAs. Oh, sorry. Just noticed a mistake that I made. I just wrote this wrong. That's definitely going to throw us off, isn't it? And it's not letting me erase it. Why isn't it letting me erase that? Okay, I'll just write over it. Hopefully you'll be able to understand what I'm doing. So that should definitely be a 2. I just literally wrote it down wrong. You can see I've got the 2 down here. I just for some reason wrote it wrong. Which does bring me to another point, which I'll talk about in just a minute. And so where was I? Okay, so I have my 6 NAs, and so I need to put a 2 right here to then end up with 6 NAs. But look at what that did for us. That gives me 2 PO4s and I have two PO4s. You'll note that I'm not counting the pure number of phosphorus and the pure number of oxygen. You can, and that's going to come out the same exact way. But that's the other advantage to polyatomic ions is that when you're balancing an equation, as long as the polyatomic ion stays together, and the vast majority of the time it will, as long as that polyatomic ion stays together, you can treat it as one thing when you're balancing. So again, what I mean by that is I didn't say, okay, two P's, two P's, eight oxygens, I didn't do that. Instead, what I said is I've got two of the entire PO4, and I've got two of the PO4. And so that's balanced. Let's look at something real quick. So let's actually bring that one back up the way that I had it incorrectly written at first. So and what did I have? I had MgCl2. So I had this, and then I accidentally wrote Mg3. So I accidentally wrote that instead. So again, so this was a mistake. I incorrectly wrote down my chemical formula for this particular combination. This is incorrect. This is not the correct chemical formula for this. Easy mistake to possibly make. You saw that I just made it here. So let's see what happens when we try to balance this, though. So we're going to start the same way that I started before. I've got 3 magnesiums on one side, 3 on the other. I'll fix that with a 3 here. That messes with my number of chlorine, so I'll put my 6 there. And so then that messes with my number of sodium, so I'm going to put my 2 here. Now I've got my 2 phosphates. So then, now I've got 3 over here. So then I start to ask myself, okay, well, how can I fix that? Well, I've got 3 phosphates over here. My 3 phosphates here, and only 2 here. Well, so I might be able to fix that by saying I'm going to have 2 of this and changing this. Oh, this is really bothering me. That's not letting me erase. There we go. So 2 there, giving me 6 phosphates total. So I'm going to put a 6 right here. But okay, now that messed with my number of sodiums. Now I've got 12 sodiums. And so, sorry, I've got 6 times 3. I've got 18 sodium. So I'm going to put an 18 there. That messed with my number of CLs. And so now I've got 18 CLs. Now I have to put a 9 right here. That messed with my number of magnesiums. And so I now need to put a 3 here for my magnesiums. Oh, that messed with my number of phosphates again. And you can see where this is going, I think. It's going to end up in this cyclical trap that I'm never going to be able to get out of. I am never going to be able to balance this equation. Just not going to happen. This is not an equation that can be balanced. Literally impossible. And so if you run into that, if you sort of find yourself in one of those traps and you keep going back and forth and hitting your head against the wall saying, I can't do this, it just keeps going back and forth and it cannot balance, take a step back, pause for a second, take a look, and be sure that you have your chemical formulas written down correctly. Chances are you don't, which is exactly what happened here. So we can see that instead, we'll get rid of all the coefficients that I have in here for now. We look at this and say, oh, okay, mistake right here. So I made a mistake there. This should be a 2. Then go through and it'll be able to balance. And so again, if you run into that scenario, you're balancing equations or you're writing the whole thing out, you go to balance it and you realize that it just won't work. There's nothing that you can do. Double check your chemical formulas, make sure they're all correct. Chances are good you've got a mistake in there somewhere. And so now pause the video and try these. Try some balancing on your own, or try some double displacement reactions. Hopefully you came up with these balanced equations. Our last type is a combustion reaction. And so for the most part, we'll be talking about the combustion of hydrocarbons. A hydrocarbon is made up of only carbon and hydrogen, sometimes oxygen thrown in there as well. Glucose, for instance, would be considered a hydrocarbon. And so hydrocarbons made up of carbon, hydrogen, and maybe oxygen will burn in oxygen. Every type of flame, everything that's burning needs O2. So O2 as a reactant is one of the hallmarks of a combustion reaction. The products will always, always, always be CO2 and water, no matter what. Those are the products of a combustion reaction. It doesn't matter what the hydrocarbon is here. Could be C4H10, like in this example, C2H6, C2H4, C6H12, C6H6, C4H8, C4H10. Again, doesn't matter what the hydrocarbon is. C6H12O6 does not matter. Your products are always going to be CO2 and H2O, and your other reactant is always O2. Always, always, always. That's a combustion reaction. Then you just have to balance it. And we see the balancing on this one looked like it ended up getting a little tricky with a 13 in there and some higher numbers. Same exact process though. You would go through the same exact way. Actually, I'll show you how I would do that. Let's work through that one real quick. So we have. So a good example might be maybe I just tell you that you need to write a balanced combustion equation for butane, for C4H10. And so this is all that you would have. And so you've got to write a combustion equation based on this. We know that the other reactant in a combustion reaction is always going to be O2. And we know that our products are always going to be CO2 and H2O. So then we have to balance it. I would usually start with my carbon. So I'm going to fix that with a 4. I'm going to save my oxygen for last because it's by itself. And so then I look at my hydrogens. I see that I have 10 hydrogens in my reactant side, so I can fix that with a 5 right here. Then I start counting up my oxygens. I see that I've got 8 here. Oh, wait, stop that. There we go. So I've got 8 right here and another 5. So I have 13 O2s. So again, what we talked about is it's okay to say that I have 13 O2s. So what I would really like to put here is 6.5. We know that we can't have 6.5, so I'm just putting that there as a placeholder so that I will then go through and double everything. I'm going to put a 2 there, double that one. Instead of 6.5, it'll be 13. And then I'm also going to double the 2 of those for 8 and 10. We have a balanced combustion equation. And so give these a whirl. Pause the video now. Try to come up with your products and then balance these 2 combustion equations. All done? Okay. Hopefully you came up with these answers. And so that brings us to the end of our video lecture on general chemical reactions. And so hopefully you have found this to be informative. Hopefully you know a little bit more about chemical equations now and how to write them, the importance of balancing. And so with that, I will bid you all a good day. And you stay classy, USM. Have a great day.